Hi class. In this video, I'm going to go ahead and solve this problem right here. This problem you can find on your textbook. It is from chapter 7, number 12. And this is going to be just a continuation of the work energy theorem that we spoke about in the last video. Okay, so here you have a car and it's going down at some speed, and that speed is 90 kilometers per hour. I've already gone ahead and did some conversions here, so just to give you an idea. So and the car was going down the highway at that speed, so that speed is going to be the initial speed. And this is also 25 meters per second, and so that you get an idea about how fast this is. It's about 55 miles per hour, give or take. Okay, so this car is just driving down the highway. Its mass is 950 kilograms, and it has to stop, and it has to stop at a distance of 120 meters for part A, right? So distance is 120 meters. So what is the physical scenario here? So what happens is that this car is going down the highway. It has some initial speed, right? But at that point, it has to stop. So its brakes, you hit on the brakes, the friction forces will slow this car down. It's going to be, it points this way, right? And then it will get to a point where the car has then to stopped. So let's say stopped here. So velocity here is 0, final. And now, and remember, this car stopped because there was a force acting against motion, right? So you have an initial motion this way, force acts this way until it stops. And let's say that this is the stopping distance. We'll call it D. And we already know what the stop distance is this number right there, right? Okay, good. All right, great. So now we go ahead and try to solve this problem. So I'm going to do something, I'm going to use this problem to do two things. One uses an example on how to compute the kinetic energy of an object, and then how to compute um, a work calculation using kinetic energy. So let's start with the kinetic energy. Let's say that we want to find out kinetic energy initial. So initial is just with the velocity initial. Kinetic energy initial, and if you remember from the last video, is 1/2 mass velocity squared. And since the kinetic energy initial is kinetic energy initials right there. So all I need to do here, this is 1/2 950 kilograms, and then this is 25 meters per second. The entire thing is squared. Okay, so kinetic energy ends up being when you carry out this calculation, you get about 300,000. It's 296,000 something, but it's close enough. Now let's look at the units. This is kilograms. Meters get squared, so that's meter squared. Seconds, second squared, divided by second squared, right? Now, this is kind of a pain to write every single time. And since energy is such a special quantity in physics, it gets its own unit. So we will define 1 joule to be equal to 1 kilogram a meter squared over second squared. So every time you see a joule worth of energy, that is hiding a kilogram meter squared over second squared. Also, this is a brand new constructed quantity. So the model for energy is a constructed quantity that includes the power of mass, length squared over time squared. Okay, so and it all gets this very special unit of joules. So up here, kinetic energy is 300,000 joules. Okay, good. Now let's look at kinetic energy final. Kinetic energy final will be 1/2 mass velocity final squared equals to, but you may have already know what this is. So if you don't already know what it is, pause the video, see if you can figure it out. And hopefully you notice that if you read the problem, calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers per hour. So it says to rest, meaning velocity 0, and we kind of already said that. So this right here is 0. Good. All right, so we got the kinetic energy initial here. Initial, and we have kinetic energy final is 0. Great. So if you remember the work energy theorem, it says that the work done is force times distance, but it also is equal to the change in kinetic energy. And remember, how we get rid of this is let's say that this is D and this is F, and this is the angle. So this is so F times D equals to F times D times cosine of the angle, right? Now in this problem we have something very special, right? We have that, so this is just a side note. So this is just a side note just to remind you right here. So this has nothing to do with the problem. This part that I just encircled here. This is just a reminder. So now let's think about our problem now. Do you see if the car started here, the distance arrow is this way. Distance arrow this way, force this way. So let me do it on the side here. So distance this way. And the force is that way. What's the angle in between them? If you came up with 180 degrees, that's a very good guess, because that's what it is. Now, try and go on your calculator, make sure it's in degrees, and punch in cosine of 180. and you should have gotten that is -1. So because of this force times this distance comes down to, this will be equal to, now specifically to our problem. So because of our problem right here in green, F times D will be equals to minus force times distance. Now this is the work, which is equal to the change in kinetic energy, which is also equal to the kinetic energy final minus kinetic energy initial. But if you remember, for our problem, what was kinetic energy final? It was 0, right? Great. So I'm just going to take this right here, and I'm going to take this right there and write it in an equation all on its own. So we're going to do and write that as minus force times distance equals to minus kinetic energy initial. Minuses go away, that's great. Now that means that the force that the tires needed to apply to this car needs to be the kinetic energy initial divided by the stopping distance. And this is 300,000 joules divided by, I believe, 120 meters. Yes, 20 meters. Before you go to a calculator, it's really easy, just do this. And there you go. Now it's 30,000 divided by 12. Let's also work out the units separately. So remember, so I'm just going to do the units separately. Joules here was a kilogram, kilogram meter squared over second squared, and this is a meter here. So what happens here is meter goes away, square goes away. You're left with a kilogram, a meter per second squared, and that just happens to be what we need, which is a Newton, right? So we get a Newton, we need a unit of force, everything checks out. So when you actually carry out this calculation, it comes about, give or take, 2,500 newtons worth of force. So when you brake from 55 miles per hour and you need to stop within 120 meters, which is about like a city block, your tires need to combined supply a force of 250,000 newtons backwards throughout the motion, throughout the entire 120 meters. Okay? Good. So now note how this here is one calculation on its own. Right here. Right? So this is how to get kinetic energy. Every time I give you anything that's moving, you can tell me what the kinetic energy is due to motion. And every time the calculation is going to be exactly like this. So what I'm going to do now is I'm going to use part B to show you how you do this problem without having to do intermediate steps, which is better anyway. So B, suppose that instead you hit concrete barrier of some sort, and instead of having 120 meters to stop, you now have 2 meters to stop. What do you suppose the force is going to be, just intuitively, before you do any calculation? Is the force that the car will experience be greater or smaller than what we found to stop the car in 120 meters? So let's see. You might or might not have an intuition about this, but let's just go ahead and do it in terms of a calculation. I'm going to start by, so let's say if you didn't want to go through the steps of figuring out the kinetic energy first, you write the work energy theorem. Work equals to the change in kinetic energy which is equals to force times distance. Now, for this problem, this will come out to minus force. Oops, no more vectors times distance. Now, this here, this part here, only for this problem, okay? Because of the way the displacement and the force vectors point. Right. So now what you can do is you can say, look, I have mass and I have speed. So if I have a mass and I have speed, I can tell what this is. And I have distance and I don't have force. So if I make, so note, if I string anything across all these equals, you can make an equation out of any of these terms. So I'm going to just take this one, and I'm going to take this one. I'm going to make an equation out of it. So changing kinetic energy equals to the kinetic energy final minus the kinetic energy initial. This in turn equals to 1/2 mass velocity final squared minus velocity initial squared. And this is equals to minus force times distance. I have both of my speeds, I have my mass, I have my distance, and I'm trying to figure out what F is. So we can do it all in one go. So F equals to mass times velocity final squared minus velocity initial squared. And there's a minus here, right? Yep, there's a minus there. Divided by 2 times the distance. And if you note, in this case, this thing comes to a stop, velocity final goes away. There's a minus here, there's a minus here, so there's a plus. So this whole thing boils down to mass velocity initial squared divided by 2 times the distance. And there you go. So let's carry out, and let me show you where all of these numbers go. Let's do this one. Okay. Force equals to mass. So we found that to be 950 kilograms times velocity initial is 25 meters per second. And you whole quantity squared, divide by 2 times the distance. Now the distance here is 100, nope, not 120 anymore, 2 meters, which I do not recommend trying to stop a car in 2 meters. We're about to find out why. If you take these numbers, if you take this number right here, you square this one, you multiply this, you will find about 150,000 newtons worth of force. And you can also note that this will definitely be units of Newton if you look at it. So kilograms, great. Meters, will be, this here is going to go square, 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 right? So meters here gets back at this square. So all you're left is kilogram, a meter per second squared, which is a Newton. Great. So everything checks out. Let's compare this number. So let's compare this number right here, 150,000 newtons, and we'll compare it to, so this is hitting the barrier and stopping in 2 meters. 150,000 newtons is what you experience, or what the car experienced. And then here, when you have a block, is 2,500. So these numbers are considerably different. And this is why you want to not crash into barriers. All right, have a good day, and you should have another video yet from me soon.